Consider the space of 2 times 2 Hermitian matrices. What is a suitable choice of field? It's obvious, right? Very easy question. Yes, of course not. But it's also not that difficult. It just looks scary if you don't know what you're doing and if you don't know the definitions. First off, how do we read this? We read this as A in C 2 times 2. This means it is a 2 times 2 matrix with coefficients or entries from C, such that A dagger, this is called dagger, looks like a dagger, like a sword, is equal to A. The question is regarding a certain choice of field, but let's leave that for a moment. What does it mean for A dagger to be equal to A? Remember, and this is something I always tell you, and that is, before you do anything with the vector space, familiarize yourself with it. If I take an example of a matrix that's in, let's take an example of a complex matrix. For example, 0, 0, 1, 1 is a complex matrix. Am I right? I'm not wrong. I mean, I'm not wrong at all. But this is not interesting. It's not interesting. Okay, what about this? This is a bit more interesting. Yeah, I do like this. So I think this is cool. But anyway, so what precisely does the dagger mean? So if this is your matrix A, then the A dagger is the complex transpose. Let me maybe write 1 and 0 here. So the first thing I do is I transpose the matrix. The rows become columns and the columns become rows. This is the first thing I do. And then the second thing you do is you now conjugate, you complex conjugate all the complex entries. So I take this I and make it a minus I. I take this I and make it a minus I, because the complex conjugate of I is minus I. More generally, if you have A plus BI, it has a conjugate which is A minus BI. We know this. So you could say that this is an extension of the class of symmetric matrices. So forget about this complex conjugation part. We're looking at all matrices. Let's just assume that we're dealing with purely real matrices, something like 1, 3, 2, 2. Then the transpose of this matrix is what? It's 1, 3, the elements of the diagonal stay as they are, and this gets switched, but they are exactly the same. So the A transpose is equal to A. This is for real entries. Now, if we take this a step further and we look at, for example, a matrix like this one, then this matrix is a very specific matrix. Does it? No. Oh. It's very difficult to find a matrix which is which satisfies this property. Give me a moment, I'll take a look at an example. Yes, there you go. So if we take this matrix, we make this an I and we make this a minus I, then first thing we do is we transpose this. Write 2 minus I, and then we write I minus 2. And then we transpose, sorry, not transpose, we take the complex conjugation. This becomes positive and this becomes negative. And in this case, your A is equal to your A dagger. So this is a very special class of, matrices, complex matrices. Not only are they symmetric, but they are also preserving to the complex conjugation operation. Of course, I don't need to worry about complex conjugating real numbers because they don't have a complex counterpart. I presume this is already clear. But I'm just now giving you an idea of the class of matrices we're dealing with. So I hope this is good. I believe this will become useful in a bit. And now, to proceed with the problem, I would like to summon my vector space checklist. Usually, we take a look at all of the properties, but I think here we're only going to look at the properties that are relevant to the choice of field. So this is a field property, and that is a field property if you talk about scalar multiplication. The zero vector, you can establish its existence. I mean, if you just take any matrix in H2C and add to it the zero vector, you get A back. But when I say the zero vector, I mean the 2 times 2 matrix which has 40 zeros. And the reason why the zero vector is in A, not A, is in H2C, is because number one, its entries are real, which means they are imaginary. Number two, it's all zeros, so if you transpose it, it's still symmetric, it gives you 0. Number three, because it's real, it doesn't matter if you take the complex conjugation. It's just a real number. You cannot really complex conjugate it. It remains as it is. And so this is how I know that this zero vector is in the vector space. I don't need to talk about what choice of field I have to be able to determine this. I already know this without, having to look at which field I'm using. Addition and scalar multiplication are commutative and associative. Needless to say, if you talk about addition or scalar multiplication in the sense of matrices, this is completely fine. Usually this is property 0 because usually it always works, nobody checks for it. But perhaps the most interesting one will be number 1. Let's get number 3 off the way. Scaling by 1 in the field yields the same vector. Okay, so let's take some matrix inside of the space of Hermitian matrices, and let's apply a 1 from the field. Which field? I could choose 1 from R, but the 1 from R is the same 1 from C. The same identity, the same identity scaling. So this is in R, and R is of course in subset of C. So I'm considering it for both of them. I'm looking at both cases where I choose the field to be R and the field to be C. Does this give me the same vector A back? And yes, the answer is yes, very clearly. Sometimes this is not obvious. Sometimes it doesn't give you the same vector back. But I'm glad this isn't the case here, because then I don't have to talk about such examples. So as I said, these are not too interesting, these cases. This is the most interesting condition. Closure under addition and scalar multiplication. Remember, we're looking to find the suitable choice of field, and then probably scalar multiplication is something we need to check, because this is the only significant element in checking that this is a vector space that involves a choice of field. And it is a sensitive area where many issues might arise. So by scalar multiplication, we mean to ask the following question. Is C times A still a matrix in H2C? Let's take, R to denote that, R will be real. So R is in R. And let's consider the other case of the complex numbers. So I scale my matrix by a real coefficient once, and the other time I scale by a complex one, and I see what happens. So clearly, the scaling by a constant would work if, by definition, R times A dagger would be equal to R times A, correct? Same thing I can say here. C times A dagger is equal to C times A. Let's take a look at the left-hand case, because I think it is much simpler. I want you to notice that this dagger operation involves two things. First thing is transposing the elements. The second thing is complex conjugating them. So if we have the entries of A as follows, and we know that A is equal to the transpose and dagger of itself. Precisely, this means that I complex conjugate all the elements like this, but also I transpose them. So I put this A3 here, put this A2 here. This is by definition my A dagger. So I transpose and I take all complex conjugates. Would anything happen if I scaled this by R? Specifically, would anything happen to the values after they get conjugated? That is a question for you. Because I think it is clear that if it's just a transpose, I think it is fine. If you multiply by a constant and then transpose, it's the same thing as transposing and multiplying by a constant. This is not really significant in determining anything. But the idea really is about looking at the complex conjugation when we multiply by R. Does it stay the same? Well, in this case, we will be switching those, right? So we will be permuting. So this will be 3, this will be... yes, this will be 2, this will be 3. Is this equal to R times A? And the answer is yes, if you're wondering, because R is a real number. So it does not take part in the conjugation process. It is not involved in any capacity. If I, for example, take the conjugate of 2 plus I, it is, and let's say I multiply by 2, it is the same thing as 2 times 2 plus I in the conjugation. Because if you think about this for a moment, you're multiplying by a real number which has zero effect on the conjugation. It doesn't change anything about the sign of the imaginary part, for example. But I think you now see where the problem might arise. It will arise specifically in this case when we take a complex coefficient. When we take a complex coefficient and we take the transpose and then we apply the conjugation, then this will precisely be the conjugate of C, right, times the matrix A. Because if you think about this for a moment, we will be multiplying by C first, and then we would, so we multiply by C, and then we would take the complex conjugate and transpose it later. I don't care about the transposition, but you transpose it, you get here 2, you get here 3. So this is C, A dagger. And because conjugation is linear in this very specific sense, so I can factor out the conjugation of C on its own and then multiply it with it afterwards. But the problem is that this is not equal to C times A dagger. In other words, when I multiply by C, it does not give me the same effect as multiplying by C dagger. It only works in the real case because the conjugation of a real number is equal to the real number. But in the complex case, we would not obtain the similar result. So there is no closure. And when there is no closure under the vector space, then problems might happen. We might exit our vector space and enter other uncharted territory. And this is often very problematic. So the space is not closed under scalar multiplication. And if it's not closed under scalar multiplication, then the choice of field to be C is imprecise, but we can choose R to be our field comfortably due to the neutrality of the real scaling property with the complex conjugation. The key word really here is just complex conjugation. If you know what complex conjugation is and you notice this very specific property, then you'll see immediately that this is not equal to that, and if this is not equal to that, and this is equal to that, then you would like this value to stay in the scope of the Hermitian matrices, but then it doesn't, because you cannot really say anything about it in that case. You cannot say with complete confidence that this thing is in H2C. That is really the problem that arises, the non-closure of the vector space under the scalar multiplication operation. So this is why it is often very important to make the right choice of field. It is not as trivial as one might think. Usually people ignore fields and they just work with vector spaces. This is not correct. A good choice of field is also sometimes very important for the success of whatever object you're trying to construct or whatever realm you're trying to function inside of. But that is a discussion for another time.